Here's module 3 for we're continuing on with the digitizing. And now we're going to look at data integrity and like the ways that we can maintain that while we're digitizing or editing our data. So this particular PowerPoint, I'll get going in the flow here soon, is to define topology and explain how topology works in editing. So what is topology? Topology is used to ensure data quality of spatial relationships and to aid in data compilation. So what that means in terms of the actual definition. So data quality means that we are trying to reduce any error that shouldn't be there. Blunders is the main one, and trying to not so much increase the accuracy of the data, but just ensure that it's available for others to do analysis on it, and they know that they can trust it. Also, when I say data compilation, and that's referring to the bringing together different layers. And so when we bring in together different layers and we have data quality issues, especially in terms of spatial information, you may have something not line up. And that makes it really difficult to do analysis with it if the data doesn't compile together properly. So what topology really does is it looks at rules that we use to maintain data integrity. And so in spatial data, right? So we're going to keep it to spatial data. And it just allows us to kind of follow a structure and a form and give the computer some rules to follow when we are editing. So the topological relationship between different features, we can use that in order to define between the different features and identify that relationship. We can look it up easier if we follow topology rules. And it really allows us to do some very nice, sophisticated, as it says, editing tools, editing. And it just gives us a little bit more to follow and allows us to, again, maintain that data integrity, maintain that data quality. So a couple of examples as we go through, just looking at kind of what does topology really do and what are some of the rules. So one of the main rules is adjacent polygons must share a coincident boundary, and that is exactly the same for both polygons. So you can see in this diagram here, we have the shape of the one polygon, and we have the shape of the other. So we have an orange one and a green one. And this green one appears to overlap into this other polygon, into the orange polygon. And so we call that an overlap. And then there's also a gap. So in between the two, you can see that the orange kind of stops here, where the green stops over here, and leaves a white spot in the middle. Now, if that is a third polygon, then that's okay. But for the most part, we usually see these gaps as like very tiny, thin gaps because somebody didn't quite put it in the right spot. So topology, this is a major rule so that both of them follow the exact same format and they stop at the exact same part. So your vertices are in the same location. Then lines have something called dangles if we don't do it correctly. So the main rule for this is that they should always end on other lines. We'll get to exceptions later, but there's always exceptions to every rule. But this one, it always ends on other lines, and if we don't, we call it a dangle. So there's two different versions. There's an undershoot and an overshoot. An undershoot means it doesn't quite make it to the line. So there's a little gap that's in between the end of this line and the edge of this line. The other one is an overshoot, where you're going to see that it kind of goes past that original line and there's an intersection that happens here. And again, it just kind of seems to hang there with nothing to like attach to it. So what we really want is both lines to end exactly on this green line so we know that it's correctly done. Another one is at intersections. So when we have a line intersection, we need to make sure that it intersects on a node. So there should be a node in this place instead of just two lines going on top of each other. So you can see here's the proper way to do it. So it's actually 4 lines instead of just 2. So we can see 1 line here, 2, and then 3 and 4. So the reason we do that is because it allows for other features to connect to that intersection. If we don't have a node there, then we won't be able to do that. And then nodes themselves should only exist where 3 lines exist, 3 or more lines exist. So we have a pseudo node if we have 2 points that kind of connect here. And I've had students ask me in the past about this, that why 3? Because we have nodes that go all the way around, like a polygon, for example, and it may not have 3 lines. We do call them pseudo nodes, so they're not actually like an incorrect term, but if we're going to call it a true node, then it means that there's 3 lines there. It's not just a polyline that kind of connects along with pseudo nodes in between. So we can't use a single line over here and have a point here. But anyway. So topology rules, again, and continuing on, there should not be copies of anything at all in your data. So there shouldn't be copies of points or lines or polygons. Don't draw over something twice. If you need a thicker line, you just assign a thicker line. So then we can get into the problem severity. So this is kind of a ranking system on how important is that particular error that if we do have one. So if it doesn't follow the topology rules, we can have one of 4 different severity levels. The first one is undetectable. It means that it's there, it exists, but nobody's going to see it. It's not like you just kind of deal with it as it comes and you just ignore it because it's undetectable, you can't really see it, and it doesn't really impede your actual map or any analysis that you do. Then there's minor annoyances, so you can go into your map, you can zoom right in, and especially if you're on a digital map, then somebody will see it, right? It's guaranteed they're going to find the error in the map, right? So this one is just kind of a minor annoyance, that's what we call it, and you just can only see it when you're zoomed in. Then there's an analysis stoppers, which is another level up, and that just means that I can't do analysis. So it either stops the tool itself and says it breaks, I can't do it, or it really doesn't allow us to do any spatial queries. And so we can't find proper relationships, and then now I've got to do a lot more complicated analysis because I can't get that data to be working properly. It didn't follow the correct rules. Those rules are like a standard across the board so that everybody follows the same thing. So if your map goes to another person, they know what to expect for that data integrity. The last one is the one that you really don't want to get into, and that is legal issues and liability. So a really good example here is parcel boundaries and ownership. So for example, if you have 2 side-by-side land properties and they overlap, who owns what part of the land? And that becomes a big challenge and big legal battle because people will fight over that, especially where the like fence lines are and everything. You hear a lot about that, and it's not necessarily the fact that it's a topology issue, but it can come up, and then when somebody goes out to the field, they're basing it on what they see on your map, and there might be overlap, and then that can come down to you, and you don't want that. All right, so as I mentioned, there's exceptions, always exceptions to rules. So one thing, as I said, like that a line needs to stop at another line. One of the big exceptions to that is a dead-end street. So, like a cul-de-sac or something, as you can see here, they just kind of stop in the middle of nowhere. They are there. They are streets. They just stop in the middle of nowhere. So it's real world stuff. It just can't follow topology rules in that case. Then the other one is that all roads end at the boundary of the data set. So they come to the end. They're not actually connecting on a line. You don't actually see them connected to a line. So again, another so-called error, but it is a real world situation. Now, one of the key things with an intersection is the fact that, like, for example, highway overpasses don't actually intersect with a particular road. Sometimes that happens when you have a bridge going over, or like for example, an overpass. So the traffic doesn't actually intersect with each other. The traffic actually flows over top. So having an additional node is actually going to cause problems with navigation systems and such, because that this traffic that's going over is not impeded. So putting a node in there is going to cause that impeded or impedance, thinking that this traffic is going to cause that a problem there. So these are considered exceptions. They don't need to be fixed. It's just real world stuff. Of course, the real world is never simple. There's always complications. So keep that in mind when you are having to digitize, that sometimes you have to do that. So in the end, with topology, we really need to focus on consistency. And this is really like, how well does topology rules mimic real world? And so an example is like looking at those rules of the dead-end streets, the intersection. Sometimes these rules are too much, and sometimes they're not enough, really. But we have to remember that if they don't reflect the real world, and they can be fixed, they need to be fixed. So we want to represent our real world. We want to represent what's on the ground. We want people to understand what we are doing, so we need to fix them if we find them. Now, if they do reflect the real world and they're not avoidable, such as the exceptions I was talking about in the previous slide, then we just leave them, and that is okay. But there are two types of models that we follow when we're trying to create these features and what we can use for analysis later. So the first one is a spaghetti model. And so the spaghetti models really don't store topology. It doesn't keep the rules, is what I'm trying to say. So these are shapefiles and geodatabase feature classes. They have no tools for testing. So if you create a spaghetti model in a shapefile or in a feature class, then you really can't test for your consistency. There are some simple tools that are available that you can use to help your features be more consistent, such as snapping, an autocomplete polygon tool, or a cut polygons tool. You can also use map topology for editing shared nodes and edges. But really, with a spaghetti model, the user is taking all of the responsibility to create the correct features when you're editing. And we'll be doing some spaghetti model work in this class. The other model is the topological models. And so these ones actually have the topology that is stored, and it sets the rules that says, yes, you have to follow these rules between your layers. And so this one is nice because you can actually test for the consistency, and it actually allows you to identify errors. So it's a little bit more advanced for advanced tools, and allows you to correct those errors, but it at least tells you what it is. The spaghetti model, you can't find those. So you guys, can fix the errors, and so you can fix the errors on your own, and allows for that manual change, which I guess sometimes, depending on the user, that can be a good thing or a bad thing. But there are poor editing techniques that have been done before, and then the user can check, find those errors, and and fix it up. So the topological models includes the coverages and featured data sets. So that's the key thing between topological models and the spaghetti models. Spaghetti models are your shapefiles and your feature classes. Topological models are in those ArcInfo coverages, which we don't really use anymore, but they had them, and the feature data sets. So in order to do checks within the topological models or to use the advanced tools, just to even do it, you do need ArcGIS Standard or the advanced license, and you guys should have access to that. So then we have complex digitizing. So this is, there's a couple methods for this. We can see, for example, we have very complex shapes. We've got like round edges and we've got curves. We've got lots of things that appear to overlap. For example, A and B have like little islands in them, and yet it's still all one feature for this feature 11. And so the way to start this is to divide and conquer, so to maintain your topology. So you start by creating the square on the outside boundary, so you can see the whole map is put into a boundary. And then you use the cut polygons tool to carve out the rest. And so that allows you to create everything within this box. The other method is adding. So if we wanted to create this, we can start with create new for the first polygon and then autocomplete for the others. So those are just two methods that you can access in ArcGIS, and the two ways to do it. Some are a little bit easier than others to do, and sometimes it depends on the data set whether or not it's going to work well or not. But you can always play around with them, give them a try in ArcGIS. So in summary, you really need to maintain logical topology, and just it says for accuracy, and that's just more so that you can use that data and everybody follows the same standard. Digitizing can and will take time. So I guarantee that in your careers you're going to be digitizing, and at the beginning of your careers you're probably going to be digitizing a lot because it is a tedious job. So just keep that in mind, go slow. If you want a really good result, you need to take the time to do it. And you need to practice it. So that's why I'm getting you to do this when we're in our assignment that's coming up. So that is everything. So finish reading chapter 8. There's no exercises, but you can complete assignment 2. And like I mentioned, you can do objective or module 4 first and then module 3 to be able to complete it. And that is everything for module 3.